Hey everybody, welcome back. If you saw the first episode, if you didn't see the first episode, well, welcome anyway. But what we talked about in that very first episode was the power supply into a circuit. Now we're starting with the basics here. There's obviously a lot more in-depth stuff that we can cover about it. But starting with the first four elements of a circuit, the power supply is absolutely critical for a circuit to work. But besides that, we also need a path for the electricity. Otherwise, we don't have a circuit. We just have a power supply. But we also need a load device. Now, unfortunately, the conductors, which is the part of the episode that we're talking about right now, is probably the most boring of all of the concepts, because usually we just kind of think about the conductors as being wires. Most of the time, that's what they are. But I'm going to try to make it a little bit more entertaining than that. And honestly, there's a lot more to it than just wires. I thought about trying to do it in some sort of a strange accent or something like that, just to make it a little bit more entertaining, but the only one that I can really do is the Smeagol accent from Lord of the Rings, and that just tends to freak people out, so I think I'll just stick with just doing it in a regular voice, but I'll still try and make it as entertaining as possible. So when it comes to conductors, we use the word conductor because conductor means to conduct electricity. Now, really, everything that has any sort of atoms, including the air around us, they're really, aside from a vacuum, isn't anything that doesn't have atoms. The idea of conducting is from one electron jumping from one atom to the next atom to the next atom. So that means really anything can conduct electricity, but the problem is we need enough voltage to supply energy to get the electrons to move. Some materials are going to be a little bit easier to sense a little bit of energy to get the electrons to move. Other materials are going to need a ton of energy or voltage in order to get them to move. So if we have to supply a whole lot of energy, then that material really doesn't conduct very well, so we call it an insulator. Now, there really isn't a line at which we say, well, this is an insulator because it has this number attached to it. And by the way, the number of whether it's conductive or insulative, we call that resistance. In fact, resistance and conductance is a term that they call an inverse. In mathematics, that just means 1 divided by. So resistance, as resistance increases, that means it gets harder and harder to move electrons. As resistance gets more and more, the ability to conduct or conductance gets smaller and smaller. So when we talk about conductors in a circuit, we'll probably use the word conductance a lot, but just thinking about that mathematically, that means as conductance gets better and better, meaning easier to conduct, that means that the resistance is going to get greater and greater. Now, resistance is usually the number that we use when we're plugging things in or measuring things. We have a resistance meter. When we plug things into equations, like Ohm's law right up here with these equations, resistance is the number that we use, normally not conductance, even though mathematically they're related. But when we talk about conductors, since that's what this whole episode is about, we'll use the term conductance a whole lot. But just remember that conductance, as it gets smaller, resistance gets larger, and the other way around. So they work together very well. Now, the idea of conducting in a circuit is really just making a path for the electricity to move from the positive to the negative, or in both directions in the case of alternating current. Now, there's a lot of different ways that these will look, and every industry, every application, small circuits, large circuits, the path for the electricity to travel is going to look drastically different. Even when you look at the little tiny green printed circuit boards, all the little wires that run at either 45 or 90 degree angles, those are the wires. Those are the conductors for the electricity to travel. If you were to take off the sheetrock on this wall, we'd probably see either conduits or wires stapled to the side, and those big wires, obviously much larger than the little printed circuit board traces, those wires are the conductors for the electricity to move. Now, even the devices that connect things, for example, when we plug something into an outlet, when we plug something in, now this outlet becomes part of that electrical path. Now, it's not the same wire, so if I plug something in, they're different wires from input to output, but now that we've established the path, it's now considered one path of conduction. It kind of assumes that we have a load device connected. Technically, if we have just a conductor wrapping around from one end of the battery to the other, that really is a circuit. It's just not probably a very useful one, and in some cases a very dangerous one, because if the conductor, which is an easy, free path for electrons to move, is just connected from plus all the way around to minus, then it becomes what we call a short circuit. And if the battery is capable of supplying a lot of current, it's going to supply a lot of current. And that can be damaging for the battery, it can make it catch on fire, it can be a safety issue. So usually we take into consideration how much electricity we're going to need to run that load device. Now the next episode is going to be all about load devices, although there's no way we can cover all about load devices in one episode. And then finally, a fourth piece of it is the control devices, because getting the electricity to move is great, but we also need to make the electricity behave properly. That might mean simply restricting how much electricity we allow, choosing when the electricity travels, like a switch. All of those are just ways of making the circuit behave and making the electrons do what we want. Those are the control devices. Neither load nor control can be covered in one episode in any way at all. So that's what's going to basically take the whole rest of the episodes. But when we talk about the conductors alone and just limiting that to the path for electricity, it usually is a little bit simpler to talk about. Now these wires, just standard wires. This one is just taken off of, I don't even remember what device this is off of, but it's regular household plug with the third wire ground, 3 conductors inside of it. And if we look really closely at these wires, we can see that this wire is made up of a whole bunch of little strands of wire. So they call it stranded wire. Now, if you look at the wire that's connecting through your house inside the walls, most likely that wire is going to be one solid bar of copper with a little plastic jacket around it. So that's called solid core. So stranded and solid wire. The difference between them has to do with how, when we think about a stranded wire, it's a whole bunch of little tiny circles that are all, if the wire's coming straight at you, you would see the end of a whole bunch of little circles. But in between all those little circles is a whole bunch of air. So really the size of the wire, the size of the plastic around it, doesn't actually tell us how much of that is copper and how much of that is the little air gap in between the different lines of copper. Now, if we took the exact same diameter of this plastic and put a solid core wire through it, a lot more of that area is wire. So there's going to be a whole lot more material. Therefore, it's going to be able to handle a lot more electricity flowing through it. So the difference between stranded and solid wire is that the same size, the same diameter of wire solid can carry a lot more electricity than that diameter of wire stranded. Diameters of wires, depending on where you're at, it's either measured in gauge, which gauge sizes are kind of odd because the smaller the gauge, the bigger the wire. It's something that it's kind of a little bit harder to think about, but a tiny number of gauge, like a 0 gauge wire, is a pretty big wire. A large gauge, like 30 gauge wire, is tiny little strands of wire. So the bigger the gauge, smaller the diameter of the wire. Sometimes it'll be measured in square millimeters. That's more of a metric term for it, but anytime we talk about surface areas, they cut that wire and then look straight down the middle of that wire, and that's the surface area that you'd see. And it's usually in the shape of a circle. The color of wire, the color of insulation around it, that's the insulation means that electricity does not travel very easily through the plastic, but it does travel pretty easily through the copper. Now, here's something that kind of takes it from the real basics of electricity, and yeah, there's wires. Electricity will flow through the wires. Something a little bit more advanced is actually the voltage that's required, or the voltage limit, the voltage tolerance of the plastic jacket of the insulation is usually up in the hundreds or thousands of volts. That means that if we put more than that voltage across these 2 wires, then the electricity will actually be able to arc back and forth between it, even through the insulation. Something that is a very high resistance or a very low conductance, which is an insulator, if you get enough voltage, you will get electricity to conduct, and it will finally reach a point where a spark jumps across. And as soon as a spark jumps across, it changes the properties of the material, and so suddenly a lot of electricity can flow. That's why lightning requires lots of volts, millions of volts to be able to jump that long distance. But as soon as it creates that huge arc, the air turns into ozone around it, which can carry a lot of electricity and drains that energy potential from the cloud to the ground. I was going to say lightning fast, but I guess that's a good pun to use. It drains that electricity really fast because it becomes a very good conductor. So it does take a lot of electricity or a lot of voltage to create that initial spark. But once that happens, if a lot of current is traveling back and forth between those, it can create a massive explosion. And in industry, that's what they call arc flash, is when an amount of voltage Sometimes it doesn't even have to get into the millions of volts. The couple of hundred, like 480 volts in a three-phase service panel, that amount of voltage arcing between two components, when you can allow hundreds of amps to flow, that amount of energy potential can create fatal explosions. That's why safety in electrical systems is such a big deal. Now, in our smaller systems with smaller voltages, there can still be sparks. It's certainly not something that we can just ignore just because it's of smaller voltage. Have you ever plugged something into an outlet while that thing is turned on? Maybe it's a lamp that's turned on or an electric griddle that's turned on, and you plug it in or unplug it and you see a little spark inside. Sometimes really old outlets will get a kind of a burned mark. You'll see the edges around these are kind of blackened and burned. That's because when you plug something in, when energy is moving, it's going to create a spark. Now, if that device is turned off, like if it's a lamp and it's turned off when you plug it and unplug it, well, there's no energy traveling. So there's no spark that's going to be created. So you can plug and unplug it quite easily. So always be careful when plugging things into outlets when they're on versus off, and that's when you see that little spark that's happening. If there is no electricity that's traveling, well, then there's no electricity that's going to travel across the spark. So it's always safer to turn things on, to plug things in when they're turned off. The smaller the voltage, the smaller the spark that you're going to get. So when we plug something in like to a USB port, USBs on a computer, these little things, they're very familiar. Everybody's seen these before. They only use 5 volts. So when we plug those in, we don't see any spark at all. However, we do want to make sure that the very first thing connected is ground. So if you look inside the connector, see if I can get a good view of that. Focus might be a little bit tough. If you can't see that really easily, go and find a USB plug on your own. Take a look inside that little thing there, and you'll see that 2 of the wires stick out a little bit further than the other 2. The 2 outside ones stick out further than the 2 inside ones. Those are the power connectors. The reason that they stick out further is because no matter how fast you plug it in, electricity is going to contact those pads before it contacts the inside pads. Those are the power connectors. So we can make sure that we're powering the device before we start trying to transmit data back and forth, mouse or a keyboard or whatever the thing is. We're trying to transmit power before we start trying to ask for data. Because if we start powering chips, sending electricity, those little tiny chips that are on a circuit board, before we've adequately supplied them with power and most importantly ground, having it a free path to flow back to ground is extremely important. If we supply power with a dead end, then sometimes that can be really dangerous because it's going to try and find an alternate path to ground, and that can go through the wrong places. So sometimes you'll see connectors where one pin sticks out a little bit further than the others. That's the ground pin. Kind of an interesting thing that we very rarely think about. It doesn't often show up. Sometimes you even think that it's a mistake in the manufacturing to see one pin sticking out a little bit further on a connector than the others. Not an accident. That one is ground. Now in this case, there's 2 of them that stick out further because we have to establish power and ground on a USB before we start transmitting data. Now sometimes, those connectors are nice in the case of USB, which stands for Universal Serial Bus, USB. So universal means that we see them all over the place. Some things are not quite as universal. I would say that the plug, the wall outlet, at least in the US, that's pretty universal. Now, universal across the world, you'll see all kinds of different profiles for plugs. So we still probably can't call this a universal. Of course, USB, universal, how many different looks to USB are there? Mini, micro, A, B, the super speed. Okay, so universal, sure, it's a great idea, but really there's a lot of different types of USB connectors, so it kind of loses a little bit of the emphasis of universal there. But we do have to be aware of what kind of connectors that we're plugging into things. Here's another thing to notice on this. See the length of those? Which one's the longest? Well, it's that round one, that's the ground connector. Establish your connection to ground before anything else. It's not a mistake. They didn't just accidentally make one of these plugs longer than the other one. Get the ground connection before you start making a power connection. We may think of plugging and unplugging as being a pretty quick process, but it's as far as electricity, things can happen, things can kill you before our reflexes can even kick in. So no matter how fast we can plug or unplug something, it can be fatal, and that's happened before. So the better we can design things to get the protection connections first, and then the power connections, well, we can do things like tripping a circuit breaker or a GFCI outlet before something fatal can occur. So I'm really glad that they put that kind of stuff into the designs. Now, some kinds of wires, this is an example of a kind of wire connection that we might find in industry. That little terminal on the end is a little crimped on connection called a ferrule. It slips over the end of the wire, and so we can see at the very end, again, the focus is not awesome here, but we can see at the end, there's a little bit of copper color there at the end. The wires, the copper wires are sticking out through the center, and this device has been crimped on to the end of it. Sometimes ends are soldered. If they don't have a connector on them, but they still have a little bit of solder at the end of it, which is just some melted metal that's been liquefied into it, they call that tinning, which makes sure that you don't have any extra little strands of wire sticking out, because even one little strand of wire sticking out when you're trying to connect all of your stuff into these tiny little boxes, one little strand of wire that's sticking out and accidentally touching something else can cause that arc and that spark and potentially explosions. So if we can get some strategies like covering it in solder, or putting a connector around it that's crimped down like a little metal shell, that really gives us a lot of extra protection. A lot of times on like automotive devices, they'll use terminals, like ring terminals and spade terminals that crimp around the end of the wire, but give you either a little circle that you can screw through a post, or a little set of forks that can stick underneath a screw. A lot of different strategies there, but the main idea is don't let it come out. Vibration is a big deal, so you can see in automotive, we got to protect against things that are vibrating, because your car is it's moving all the time. So if we have something that can vibrate loose and cause a connection problem, we really want to make sure that that's taken care of in advance. For some things, especially when we're experimenting or called prototyping, sometimes we'll run across connections that are a very specialized kind of connector, like these, or sometimes they're bigger ones that they call banana connectors, kind of because they have a little bit of a curved shape to them, like a banana. They can be connected and sometimes stacked like this one. These can be stacked together. They usually aren't meant for permanent connections. They're meant to create temporary connections so that we can either experiment or sometimes troubleshoot. It looks a lot like the end of a multimeter. A multimeter, like a voltmeter, is never meant to be a permanent connection. It's meant to be something where we just make a connection in order to make some tests and then remove the connection. So they're temporary only, but that means we also have to have matching connectors for something to plug into. The more permanent connections are the ones where they're soldered or terminals are crimped onto the end and then torqued down using appropriate tools. And sometimes when we have wires that are connected to a circuit board, those green circuit boards, we'll just see big rows of pins sticking out the end. For those rows of pins, they're called headers. A lot of times we'll have connections that are multi-wire connections, but they'll connect very easily to those rows of pin headers. Those pin headers can have different spacings. Some of them are just these rows of giant pins sticking out of it and would be way too big for these to connect. Sometimes those pins are really tightly packed and extremely close together. If you've ever taken apart a laptop, look at the little connectors, the little headers where like your keyboard and the monitor plug, the screen plug, what those ones fit into. Sometimes those are just tiny little press-in connectors that are extremely small. But regardless, our whole purpose in this is to get the electricity to go from one set of pin headers around to the other side. Lucky for us, if they use different wire colors, that makes things a lot easier to trace. A lot of times in industry, there's certain wiring standards, as established by NFPA and some certain standards in the National Fire Protection Association, NFPA 70. Those wire standard colors can actually lead to sometimes some pretty confusing situations. Like blue is the appropriate standard for powered 24-volt DC connections. Well, most control systems are powered by 24 volts DC. And sometimes there can be hundreds of devices connected. So you open up a control cabinet and it's not unlikely to see hundreds of blue wires. And most of the time they'll put a little label at both ends and the devices that they're plugged into to give them an identification of, okay, you look at this end and it says wire 1013, and you look at the other bundle of wires and okay, we found 1013. So usually makes it pretty easy. Of course, you always say it should be that easy. But you find out in reality, it's often equipment that was designed a long time ago, or it's had to have been fixed, and okay, we didn't have the right wires, but we just need to get the machine up and running. So there's a whole bunch of blue wires and one yellow one, because that's all we had at the time, and nobody bothered to go back and fix it. So sometimes what should be the case and what is actually the case are very different from each other. But knowing those standards is definitely something to keep in mind. It can definitely make things easier or more difficult for somebody later on down the road. Sometimes we have these connectors where they're round at the end, sometimes power connections, sometimes, not often, but sometimes those can come from USB cables that have this connector at the end. They call it a round barrel connector. In the last video, we looked at a barrel connector that came out of a car, an automotive connector, and it had a little indicator that said center positive. So be careful on these barrel connectors, which one is the ground and which one is the positive, because connecting something that's positive voltage to a ground connection in the wrong place can cause a short. So if for some reason this outside is positive instead of the center being positive, if you accidentally let that outside positive touch another piece of metal inside a box somewhere or in that car, it just touches something else that's metal, that's when that spark can happen, blow fuses. Well, hopefully it'll blow fuses and breakers, but if it hasn't been properly designed, instead it can start harming all the other components in the circuit. So we got to be really careful with that. Most of the time, the inside of the tip is positive, center positive. That way it is much more difficult for something to accidentally come into contact with it. The outside being ground, well, everything else around you is already grounded or should be grounded, so it's a lot safer. Now, a lot safer does not mean always safe. That's something we should never say in electronics. Is the situation always safe? No, it's never always. We always have to go into it thinking what could go wrong and how can we protect ourselves against that. But I guess that's the case in everything. Even when you're driving down the road, you should always be thinking, well, yeah, everybody should be driving properly. But if they're not, what could go wrong and how can I protect myself against it? So that's really the whole principle of safety. Now, sometimes these connectors, especially multi-point connectors, still have some standards. This one is coming from an, usually in this case, it's an RS-232 connector, or a serial port is commonly what they were called. They're serial parallel ports. We don't find them as much anymore, but they are pretty common sometimes on industrial equipment. Now, serial cables are just a whole bunch of straight wires going through a jacket. In this case, there's 9 of them. Now, USB is actually the same thing, but there's only 4 of them. But they're all straight 4 wires side by side traveling through an insulated jacket. Interestingly, on those cases, since it's a whole bunch of wires side by side, there's some amount of resistance to electrical flow, but more importantly than that, in between 2 sets of wires that are running side by side in a cable, if we apply a voltage to those wires, then some electricity is automatically going to travel between the 2 by a concept that we call capacitance. When things change, electricity is able to flow easily through a capacitor. Now, a capacitor is just 2 conductors separated by an insulator. That's exactly what 4 wires traveling through a wire is, 4 conductors separated by insulators. They're capacitors. The longer we make those wires, the more capacitance is going to build up. So in these old serial cables and USB cables, there was only a certain distance we could go before we started running into problems and it just failed to communicate. So USB cables are never that long. You can get extenders for them, but they're only a couple of feet long. You start stacking up a couple of those, your stuff won't connect anymore. But they had to somehow overcome that because we needed to send computer signals back and forth over longer than just a few feet. So that's why they came up with twisted pair wires. And they've been around for a long time. Now we call them Ethernet cables most commonly. But the twisted pair wires, if you take off the insulation around it, you'll see that every bundle of wires is twisted in pairs. This is why we call it twisted pair. Well, when wires twist around each other, it introduces something called inductance into a wire. Inductance does exactly the opposite of capacitance. If capacitance was our problem, let's introduce some inductance to get rid of that. Now we can make these wires travel much further by just perfecting and tweaking the exact which wires are twisted and how fast do they twist, how many twists per inch. Very interesting study on how we can get wires to travel much further to get computer communication to happen while also counteracting that capacitance problem by introducing something new into the circuit to solve something else being introduced into the circuit. Usually introducing more stuff into a situation is bad. In this case, it's pretty productive. Now, the difference between conductors and load devices is also where things start getting a little bit tricky for those that have already studied electricity a little bit. Because a load device is really just a way of resisting the flow of electricity by converting the electrical energy into something else. In a motor, it converts it into mechanical energy. In a light, it converts it into light. Heater converts it into heat. The whole purpose of the load device is to make it electrical energy turned into something else. Those devices are always some form of resistance introduced into the circuit. That's why the load device automatically restricts how much current is going through the wire. But we also said that some materials are better at conducting electricity than others, and honestly, there is no material that is perfect at conducting electricity. Sometimes they'd refer to that as a superconductor, but there really is practically no such thing as a superconductor. Even a wire, even a gigantic triple-aught gauge, huge solid core wire is going to have some resistance. But load devices also have some resistance. So what's the difference between a load device and a conductor? And honestly, the difference is there's usually more resistance in a load device. That's the extent of the difference. So this is a little bit more of an advanced subject because it kind of separates, instead of being separate concepts, conductor and load device, we have to really pay attention to how much load that wire is actually putting into our circuit. It's no longer just a conductor that freely allows electrons to flow and restricted by a load device. It's actually a conductor that's restricting the load and a load device that's restricting the load. Just usually the load device restricts it more. Now, to kind of prove that that's true, it's easy for me to say that wires and load devices are about the same thing. But if we take a look at this is that typical, here's some strands of wire. Okay, it's some conductors. They're big wires, well, relatively big wires. You can certainly find some a lot smaller than that. They're stranded, but I see a whole bunch of little strands making up one conductor. Now here I have a three-phase motor. It's heavier than it looks, but if you look closely at it, inside it is a bunch of little sets of stranded wire. And this is a bunch of lines of stranded wire. So what makes these different from each other? And honestly, there really isn't anything that makes these different from each other, except that this has been specifically designed to do something useful. In that case, generate an electromagnetic field that rotates something inside. It's a motor. That's what motors do. They're just big coils of wire wrapped around some metal cores that generate an electric field or a magnetic field. So they're no different than a conductor. Usually, though, the load device has more resistance and is therefore more responsible for converting the energy into our useful output than the wires are. So when we design a system, we look at our load device. We say, how much energy do I actually need to convert in order to get something to run? How much energy do I have to convert and how fast? That's called power. And power can either be measured in horsepower or watts. Sometimes kilowatts for big stuff, megawatts for really big stuff. So I say, how much energy is that load device going to use? And therefore, what are its properties? What voltage do I have to supply to it? And I can calculate how much resistance I'm going to need based on how much current goes to it and what the voltage supply is. Here again, we have some pretty simple but useful equations that can tell us if I got to supply this much voltage and it's consuming this much current, this must be its resistance. So if I know the resistance of my load device, it can help me choose the appropriate conductors to get electricity there without adding more resistance, which would use up too much of the energy. Now, what happens if we use the wrong size of conductors then? And this is actually something that pretty commonly happens with extension cords. You may have run into this problem before. I know I have. It's easy for me to say, well, yeah, I know how to properly size them, but sometimes I just have a small extension cord laying around and I need to run my air compressor. So I plug it in and hope for the best. Now, what I've run into before, and likely you have as well if you've been in this situation, you grab an extension cord that's not rated for the amount of current that should be, but it's all you've got, and you need to run your air compressor to fill up some tires in the car. So you plug it in, and the motor on the air compressor starts kind of kicking in and just can't quite get up to speed, and then a breaker inside your house trips. Well, what's going on? Well, why did it do that just because we used an extension cord? And some people I've talked to about this, and they go, yeah, I just went and found a different extension cord, and it was exactly the same length, and it worked just fine. The reason for that is because if we have too small of an extension cord, then there's too much resistance in the wire. A lot of that energy going through that wire is being converted into heat. In fact, sometimes you can feel at the ends of a wire when it plugs into the wall. Sometimes they'll be really hot. You know that that's probably not the right size of wire to use for that situation. So if the electricity is being shoved through that wire and too much of the energy is being converted into heat, then the motor also is asking for a lot of energy. And so first of all, it doesn't have enough voltage because too much of the voltage is lost in the wire. Not enough is left for the motor to finally kick up to speed. But also, as that motor is trying to turn on, it needs more current. This is especially a big deal with motor devices because they take more current to get up to speed. And so it's pulling a lot more current because the wire is restricting the amount that can get to it. So it has to pull more, and that's overloading the breakers and causing the breakers to trip. So you go and either switch it with a shorter extension cord, which means less resistance because the electricity, every new foot of wire that electricity has to go through is more resistance. Decrease the number of feet, and now you can start the motor. Or we switch to a bigger extension cord, and now we can run the motor. If you have to wire something to an outbuilding that's going to be using a certain amount of current in a panel, they'll always tell you what size of a wire gauge you must use if it's going to be greater than a certain distance. And the reason for using that extra wire gauge, the bigger sizes, is because we have to make sure that we're not restricting the electricity getting to that outbuilding because it's a much longer distance. So length of wire and diameter of wire are really a big deal when we talk about conductors. Another one is the property or the material that makes it up. Commonly, the most common materials to see for conductors are aluminum and copper. Both aluminum and copper are pretty good at conducting electricity, but there are slight differences. So you see these big tables that say if it's aluminum wire at this gauge, you can go this far without having to use this size of wire. And if it's copper, then there's another list of tables. And most people don't memorize tables. They just have to know where to go to find the information that's on those tables. So very useful to know. Also, one last note on conductors. Even though conductors theoretically are the whole run is the same kind of wire, so we just say, well, it's this many feet. Anytime we have to go through a connection device, the point to be really careful about is that those connection devices have some sort of method of connection. Now, in this case, it's screw terminals. Sometimes on some outlets, it's just poked straight into the back usually only for smaller wires. Sometimes those will be 14 or 16 gauge or more, which are smaller wires. So for larger wires, we have to use the screw terminals on the side. Now, if you don't screw that in tight enough, then that means that there's not a whole lot of metal-to-metal contact. It's not being squished enough. So really think about it as going through a nice open pipe, and then all of a sudden that pipe gets really restricted and then opens back up again. That connection point can be the restriction in the pipe before it opens back up. That restriction point is going to be losing a lot of energy and can be heating up a lot. So if we don't have proper connections, proper tightnesses of connections, if it's a spring type connector, make sure that it's a good connection, because if we don't have that good connection, that can be a point where heat is being generated and energy is being lost. So you might be supplying that 120 volts into the circuit, but if you have one very, very poor connection, sometimes it's even underneath those wire nuts, if it's a poor connection, it may be losing a lot of that voltage, and so your load devices don't get the amount of voltage they should. So things might not turn on, or it might just act really oddly, because you can't say it's not getting any electricity, it's getting some, but it's not getting a free flow of electricity like it should, because connection points can be weak points in a system too. So conductors. In summary to the conductors, there's different types of materials, and conductors are the ones that allow electricity to flow most easily. Insulators are those ones that don't allow electricity to flow, but we should never exceed the voltage rating of an insulator. Conductors are most often wires, and those wires are screwed or clipped or crimped with some sort of connection method between two ends. We need to make sure that those wire connections are solid, that they're clean and free of corrosion. Every once in a while, you might have to take off a connector and use a wire brush or replace the connector. If there's any sort of corrosion, or in automotive stuff, it's a lot of times grease buildup in between connectors. And we have to make sure that when we're using connectors, we're aware of which one is supplying the energy and which one is the ground. Because the conductor that's supplying energy, if it accidentally touches anywhere that's ground directly, that's called a short circuit and can cause either problems, health problems, safety issues for you, or can risk damaging your equipment. Either of those are bad situations, although I'd say the personal safety one is more of a factor for you to take into consideration. It's expensive to replace equipment, invaluable to replace people, so always be careful with what you're doing. Larger voltages means that we can get bigger sparks, and as soon as a spark is established, a lot of electricity flows and a ton of energy is pumped out of that situation. That means that we get an arc or an arc flash or a giant spark if the potential, voltage and current, is high enough from a particular energy source. We also have to be careful that the size of the wires and the length of the wires that we're using are appropriate for the load devices. The more energy that a load device uses, most likely we can think about motors. Motors are a big usage of energy, lights sometimes too. But if the load device uses a lot of energy, you have to use a large and short length, big gauge, short length, appropriate conductor in order to get electricity to supply that. So in our next video, we're going to talk about those load devices a little bit more in depth and start talking about some of these equations, like knowing how power relates to the amount of voltage and current and therefore the resistance that we can use to evaluate our situation. When we talk about conductors, the best we can do is say we got to look at the load devices in order to evaluate what conductors we need. But it's a very important concept regardless. So I hope you stay tuned. I hope you enjoyed this one. We'll be looking at a lot more in-depth discussions about this kind of stuff. But as always, if you have any questions, feel free to comment or ask, and I'd love to elaborate on those more. And I hope you have as much fun learning about this electrical stuff as I do, because if you can't tell, I really enjoy this stuff, and I hope you do too. So see you next time. Stay tuned.